Alright, welcome guys. If I is a subset of a ring, it's an ideal which is just like being prime, really. If I is additive, which means that it's a plus group, and R times I is contained inside of I. Now if we assume commutative, then we don't have to say the other way, but without commutativity, it requires this process. Now what's neat about when you have a ring that has an ideal in it, then you can form R mod I, which is the cosets of I, and the additive action would be K plus I plus M plus I is just add the names, and the multiplicative action is K plus I times M plus I is just Km plus I. So you've seen this before. This is just like what we did originally with Zn, and we created our modular classes. So we are going to mimic the integers. So the integers are really neat in the fact that we have primes. Well, what we're going to do over here is we're going to start with a field, Q, and we're going to put this to be finite polynomials. So you know that a finite polynomial over Q plus a finite polynomial over Q adds. And you know that a finite polynomial over Q times a finite polynomial over Q multiplies. So this is a very nice set. In fact, the negatives are just the negative of the polynomial's coefficients. 0 is the zero polynomial. There are tons of neat things about this. And what's kind of neat about here is the primes are the irreducibles. So if you pick an f of x in Q square bracket x, if you believe you can't factor it, then it's much like a prime in the integer. Now, we're going to use one special theorem that we're not going to prove. It's called the rational root theorem. And it says the following. If f of x is an element of Q square bracket x, and f of x is equal to a naught plus to an x to the n, so the degree of f is equal to n, the theorem says f has a root in Q if and only if. Now, if you think about what we remember about factorization, you know that the linear factorization of ax plus b, the a's got to be involved in somehow this term, because the ax is going to multiply times another polynomial, and the b's got to be somehow involved in this. And this is if and only if that root is an element of the root on the ax plus b equals 0 says that the a ends up in the bottom. So this is factors of the leading coefficient, and up here is factors of the constant. Now, over here, how we determine primes, well, we have lots of different tests. There are tests similar to this, but this is basically what a prime looks like in a polynomial field. So let's just take a look at how this theorem would be used. For example, f of x equals 3x cubed plus 6x minus 1. That's clearly an element of Q square bracket x. And if there's a root, then f of r equals 0, r in Q, if and only if r is an element plus or minus. And now you ask yourself, what are the factors of the leading coefficient? Well, it's 1 or 3. And what are the factors of the constant? Why, it's 1. And so R has got to be 1 or 1/3 plus or minus. Now that's easy to check. Just evaluate it. Let's put in 1. Lo and behold, we get 9 minus 1, we get 8. Nope, doesn't work. Put in minus 1, we get minus 10. Doesn't work. We put in 1/3. Now that could get interesting because 1/3 cubed is 1/27, 1/9, but then 2 minus 1. Now, looks like this is always going to be a fraction when we plug that in, so this is not going to work. So, therefore, we conclude that f of x is irreducible over q. It can't be factored. So, irreducibility is an unfactorable polynomial over the given field that you're working with. So this is much like a prime in the integers. Now, if you remember when we were in the integers, and we did z mod multiples of n, that said we had cosets of a plus multiples of n, and what we realized that if a was really big, let's say a is bigger than n, then we could write this as, well, if a is bigger than n, then we take a minus n plus multiples of n, such as a is in the integers. And, well, that can be any multiple of n plus n is still a multiple of n. This is the same as a smaller coset. Well, an example of that, for example, would be z mod 11. And I could ask for the coset of 17 plus a multiple of 11. Well, that's the same as 6 plus 11 plus a multiple of 11. Why, lo and behold, is 6 plus 11. And how do we think of this? Well, we wrote this as Z11, and we wrote 0 bar, 1 bar, all the way up to 10 bar. And what this calculation with cosets is that 17 bar is really 6 bar, and bar represents that we have taken a coset operation. It's really the same thing. So this is the abstract form of everything in a coset, and then we can reduce it to a canonical form. So we know how to reduce to canonical form in the integers. We just get it down small enough. How is that small enough actually generated in the integers? Well, if we're doing this, when you have some number k and you want to reduce it down, you don't want to say, I keep subtracting n, keep subtracting n, keep subtracting n. What we can do is we can quote the division algorithm that says k is equal to some quotient times n plus a remainder, and the remainder is less than n but greater than or equal to 0. This was fundamental, and this allows this k to be written as r plus q times n plus multiples of n, and this absorbs inside as additive, and so it's r plus multiples of n. So the reason that k bar equals r bar, and r bar is the right way to express it, is that we had the division algorithm. So now the question is, how can we do the division algorithm for q of x mod all multiples of a polynomial? But in order to be analogous, that polynomial needs to be irreducible. So let me do an example of this. Very simple quotient ring calculation. We know that x squared plus 1 doesn't have a root in the rationals. Very easy to check. 1 doesn't work, minus 1 doesn't work. That means that this is all possible polynomials plus any multiple of x squared plus 1. And the h of x is just some q square bracket x. That means this is its abstract form. That's what this looks like. But that abstract form isn't exactly what we want. Let me give you an example. X cubed minus 1 is an element of q square bracket x. Should we call its cosec x cubed minus 1 plus multiples of x squared plus 1 its name? And the answer is yes, it's legitimate. But what we do is we do long division, or the division algorithm. So watch this. I'm going to take x cubed minus 1, and I'm going to divide it by x squared plus 1, and I'm going to say how many times x squared go into x. Well, it goes in x cubed, it goes in x times. X times x squared is x cubed, x times 1 is plus x, and then we subtract. And that'll bring x cubed minus x cubed, and then we'll have a minus x minus 1. And that's smaller than that. You remember doing this? Well, what does this say? It says that x cubed minus 1 over x squared plus 1 is the quotient plus the remainder over the divisor. So if you believe in long division, that says that you actually believe in the division algorithm for polynomials. So, the division algorithm for polynomials of a field square bracket x exists, and it looks like this. H of x is always equal to a quotient times the divisor plus a remainder. But what's what we are going to require of the remainder? Well, just like over here, we required the remainder to be smaller than the divisor because that's what this is saying. Realize, k divided by n is the quotient plus the remainder over n. This is how we've been thinking of it. This is how we wrote it. Well, this is how we're thinking of doing long division. This is how we write it. And the only requirement, if we've done it right, is we want this sucker to be smaller than the divisor. Well, it turns out that for polynomials, the very natural thing is that the degree of the remainder needs to be smaller than the degree of the divisor. And it's perfectly fine if it's equal 0. That means the r of x is a constant. That can happen. The two constants have degree 0. So, what does this mean? Well, it means that if somebody takes an f of x from q square bracket x, and f of x is irreducible, that is just like having a ZP construction, Z mod P. What does it look like? Well, it looks like this. Q square bracket x mod all multiples of f of x, whose canonical canonical representation is an r of x plus a multiple of f of x. And what are we going to require? We want the degree of r of x to be less than the f of x and possibly positive. Why? Because now canonically we know that you do long division by f of x, so anything that's listed as too big can be listed smaller. So in other words, our x cubed minus 1 plus any multiple of x squared plus 1, by the long division that we did, x cubed minus 1 was really x times x squared plus 1, q of x times the divisor, plus the remainder. But because the ideal, all multiples of this, absorb this, these add, this plus that is inside of I. This is the canonical name of this coset, and its degree is less than the degree of 2. So how many things really live inside of here? Well, q square bracket x mod x squared plus 1 has to be remainders upon dividing by a quadratic. Well, it looks like a plus bx plus all multiples of x squared plus 1. So how do you work with that? Well, let's just do one of them. Ready? Let me take 3x plus 1 plus all x squared plus 1 And let's just add it to 4x plus x squared plus 1. Well, the addition says just add the names. When the names are in canonical form, why, they just immediately stay in canonical form. And just like that, we have the addition. Very trivial. Now, that's kind of special about polynomials. If I take 7 plus 8 and get 15 and I'm Z11, I have to move it down. Can't happen with polynomials because degrees can't go up. However, if I want to multiply these two, you multiply the names. This absorbs in there, this absorbs in there, this absorbs in there. This ideal property, the i's just suck everything in. This is going to be 4x times 3x plus 1 plus any multiple of x squared plus 1. But this is going to be 12x squared plus 4x plus any multiple of x squared plus 1. So now you should do a canonical decomposition of this by dividing by x squared plus 1. I'm going to demonstrate that it's not hard to guess at what it really is. 12 times x squared plus 1, why, that's 12x squared plus 12. So I think if I write 4x minus 12 here, I want you to take a look. 12x squared plus 12 minus 12, 0, 4x. This is exactly that. So I have a little trick method of doing long division in my head. But x squared plus 1 divided in that goes in 12 times, and that's the remainder. Now, this additively moves inside of the ideal. All multiples of x squared plus 1 plus a 12 multiple of x squared plus 1 is another multiple of x squared plus 1. And lo and behold, we get 4x minus 12 plus x squared plus 1. And just like that, this times that is this. And it's back canonically inside of our polynomial. Well, this is really neat. This says that when you have a field, when you have an irreducible polynomial, it has a canonical representation, provided these are all multiples of that as an additive absorptive set, and the degree is less than the degree of the irreducible, which is greater than or equal to 0. You have created a ring that has addition and multiplication. We would love to know if that ring is really nice. How good is this? Well, if it's really good, it has no zero divisors. Sorry, if it's good, it has no zero divisors. If it's really good, it has inverses. So first off, let me take an r1 of x plus an f of x, and multiply it times an r2 of x plus an f of x. And I know that that's r1 of x times r2 of x. Is there any way that this can be 0? In other words, could this be a multiple of f of x? If it is, that would be bad. We don't like a ring that has that property. Well, it turns out that all that's required to prevent this is two things. One is that f being a field says we can't have coefficients disappear. The degree of this is the sum of the degrees of these two expressions. And for us to get 0 says that this has to evenly divide that, and what this says is it boils down to that f is reducible, and that's a contradiction. So when we have a field here, we maintain the degree, and when we have all multiples of f of x here for our ideal, then we can't get 0. So this is not possible because f of x is irreducible. So now that we know that this doesn't have 0 divisors, the next question is, does it have inverses? Well, I'm going to do it for the rationals, and it's not too terribly hard. So let's start with f of x, irreducible, in q square bracket x, and we build the cosets, q square bracket x mod f of x, and lo and behold, We then express it canonically as remainders plus our f of x's, such that the degree of the r is less than or equal to f, but greater than equal, less than the degree of f, but greater than equal to 0. And now I would like things to have an inverse. Now, once again, we think back to our days in the integers. Why in ZP did 5 inverse exist? We should call 5 bar. How did that happen? Well, what we did is we first looked at 5 and p in the integers, not in ZP, and we said, oh, the GCD of this is 1 because p is prime. And so that said we wrote 5 mu plus p lambda equals 1, and this was an equation in Z. But then we read it in mod p, and we get 5 bar mu bar plus p bar lambda bar equals 1 bar. But this was 0, and we get 5 bar mu bar equals 1. And we have found the inverse of 5 in some ZP where p was bigger than 5. Well, can we mimic this here? So let's give it a try. So we have the degree of r of x less than the degree of f of x. And first off, let's note that if this is a constant, its inverse is in Q, it's reciprocal. So let's have this greater than 0, because if it's constant, it's if r of x equals 3, well, then r of x inverse will be 1/3. Even as a polynomial, those two multiply and give you 1, so it's very nice. So what happens when we have this r of x? Well, r of x and f of x, the GCD of them is 1, because f of x is, lo and behold, irreducible. So what theorem do we need? Well, we need the theorem that says that this is possible. Well, guess what? Exactly that theorem that we did here works here. There exists a mu of x and a lambda of x such that mu of x, r of x, plus lambda of x, f of x equals 1 in RQ square bracket x. And then when we read it modular RF of x, this becomes 0, and we have found the inverse of r of x. So let me demonstrate how that works. Remember, to find the GCD, wasn't that the Euclidean algorithm? We did long division forward, and then we did it backwards. Can't be that hard. So let's do 3x plus 2, an element of q square bracket x mod x squared plus 1. I should put a bar on this, right? So I have 3x plus 2 plus x squared plus 1 is an element of this q of x mod x squared plus 1. Very exciting. And now, this action is called lifting, going back to where we were before. We're going to go back to where everything began and said, I have 3 of x plus 2, and I have x squared plus 1. They're both in q square bracket x. And we remember that in the integers, we took the large one, divided by the smaller one, got the remainder, and then we moved them over. Let me give you a little reminder. 13 and 8 have a GCD, which is 1, which says that 13 is 1/8 plus 5. Then we move the 8 over, we move the 5 over, and we said, well, how many times did 5 go in there? 8. Once plus 3. Then we move the 5 over, we move the 3 over, and we said 1 times 3 goes in 5, 1 times plus 2, and then we move the 3 over, and now when we're down to 1, we write this backwards, and we can figure out how to express 1 as a linear combination of 13s and 8s. So let me do that backwards. 1 equals 3 minus 1 times 2. But 2 is equal to 5 minus 1, 3. 1, 5, and 1, 3. Why, lo and behold, that's 2 3s and 1, 5. Now, how do I know to do it that way? Because this equation had the focus of 3's and 5's. Now I go back to the 3. And I say, oh, 3 is the same as 8 minus 1, 5. Minus 1, 5. And this is 2 8s minus 2 5s minus 1 5, which is 2 8s minus 3 5s. And again, 69. Excellent. And now I go up to here and say, what about that? I'm trying to make room. So now I have 1 is 2 8s minus 3 13ths minus 1 8. I'm now going to finish 1 is 2 8s minus 3 13ths plus 4 8s, 4 and 8, 6. 1 is 6 8s minus 3 13ths. Is it 6? 3 times 1 is 3. 3 8s and 2 8s is 5 8s. And is it true that 40 minus 39 is 1? You bet it is. What have we actually just done? Well, we've actually done, if 8 bar is an element of Z13, 8 bar inverse, lo and behold, is 5 bar, because this goes away in Z13 and you get 1 bar equals 5 bar times 8 bar. We've discovered their inverses. Now this is a bit messy. How messy can it be over here? I am not going to say every good mathematician can make this problem harder. It's going to be hard enough, but here we go. So the idea is we start with the larger one and we divide it into the other one. And I believe that 1/3 x times 3x plus 2, that is going to be x squared. It's also going to be 2/3 x, so I want to take away 2/3 of x and add 1. And do you believe that this is balancing? Let's take a look. 1/3 x times 3, 1/3 times 3 is 1, x times x is x squared. I have a 2/3 x, but I've taken it away, so that's gone, and I have a plus 1. Indeed, this balance. This is a short way of doing long division. Now, if you wanted to do it over here, if you want to take 3x plus 2 and long divide into x squared plus 1, you would have indeed have gotten 1/3 x and then this remainder. But that's not smaller than that. I'm not quite done. I got the first part. But it turns out you don't have to be super, super accurate on that. It's enough to get the first one. I'm going to finish this over here. 1/3 x times 3x will be x squared. 1/3 x here will be 2/3 of an x. And then when we subtract, we'll get the minus 2/3 x plus 1. But that 3x can go into there, right? What times 3x will be minus 2/3 x? And the answer is minus 2/9. So if we have that in there, plus 1/3 x minus 2/9 of 3x plus 2, well, that will get rid of the x squared. And the minus 2/9 here will be minus 2/3 x, and we'll have minus 4/9. When we subtract, we're going to get 13/9. Now, why did this help me do this? Because it helps me see the adjustment I have to make the solve work. Now, the hard part about this entire calculation is that it's okay not to get 1 here. So now I'm going to write down what I have. That's what I had just learned. What does this say? It says that x squared plus 1 minus 1/3 x minus 2/9 times 3x plus 2 is equal to 13/9. Now, if I want to read this in q square bracket x mod x squared plus 1, It's like putting a bar on this. Well, this will become 0 plus x squared plus 1 because it sucks in. This will be minus 1/3 x minus 2/9 plus x squared plus 1 times 3x plus 2 plus x squared plus 1. And this will be the same as 13/9 plus x squared plus 1. So now if I just multiply by 9/13, so 9/13 of minus 1/3 x minus 2/9 plus x squared plus 1 times 3x plus 2 times x squared plus 1 will be 1 plus x squared plus 1. This guy, we have its inverse. 3x plus 2 bar inverse is 9/13 minus 1/3 x minus 2/9 bar. And you can multiply them out and check that you actually get a multiple of x squared plus 1 plus 1. And so it'll be 1. All right. So what does this say that we have done? It says we have mimicked z, found a prime in z, formed z mod p, and we often write it as zp using bars. When we start with q, square bracket x, and we find f of x irreducible in there, then q of x mod f of x is like zp, and it becomes a field. It is additive, has inverses, has 1, and most importantly, if this is commutative, we have created a field. But what's even more crazy here is that there's a special element in here, x plus f of x. And when you view f of x as being in this larger ring by changing its coefficients through the embedding, that's actually a root to our new f of x, which is really crazy. And that's what I cover in the final. Now, I do want to cover one more small bit. And here. Well, it seems that I've run out of paper stock that I wanted. I will have to reuse a couple of ancient sheets. So, we started with z, found a p, we built z mod p, which we called zp. If we start with q, join square bracket x, and then find an irreducible and build this, it's analogous. But this special element, x plus f of x, is a root in q square bracket x mod f of x that actually solves a new f of y, which is the same one, but we write the coefficients in here with a y with different powers. It actually solves it. Well, we wrote how to do this once before. If we have a field and we have a polynomial that we want to solve, if it's irreducible, and we assume f of alpha equals 0, we adjoin alpha. But here's the general part of this construction. It depends upon the degree of f, how much of the alphas have to be written. So for example, when we wrote f of x equals x squared plus 1, then this extension was by a alpha plus b. Why? Because upon long division, we didn't need any remainders bigger than linear, and that's a linear. But if I had taken q of x and picked f of x equals x cubed minus x minus 1, I think that's irreducible, 1, 1, yep. Well, then if f of alpha is equal to 0, then what is q adjoint alpha? Well, again, it's the remainders upon dividing by x cubed minus 1, which means you need to write down a plus b alpha plus c alpha squared. The a, b's, and c's are in q, but you also have to say that alpha cubed minus alpha minus 1 equals 0. There's a relationship. Now, this can be much easier than that to calculate. So let me give you an example here. Suppose we're doing this one, and I just want to take 3 alpha squared plus 7 times alpha squared. Well, I just multiply it out, 3 alpha to the 4th plus 7 alpha squared. But then I use this equation to say that alpha cubed is alpha plus 1. And I replace one of those. And I get the expression here, what is it, 7 alpha squared, I get 10 alpha squared plus 3 alpha. This reduction is part of what long division and the modulus effect does up here, which can be very complicated. But down here, it can be very simple. So we actually have two ways of understanding this, and this is very important, and that is, one way is just a made-up root, and it has properties in which they relate, but the other one is a constructed root, but it's much more difficult to write. So this upper world is tougher. Now I need to point out, it is really, really imperative that when we write down these f of x's, that if this new system is going to be nice, it has to be irreducible. Absolutely has to be irreducible. Because if you did something like this, x minus 1 times x plus 1, which is x squared minus 1, and you said I have q adjoint alpha, where alpha squared minus 1 equals 0, then the weird thing is this set here, a alpha plus b, and b and q, is not a nice set. That relationship says that alpha minus 1 and alpha plus 1, which would be in this number system, when they multiply together, get 0. And this number system here, therefore, has 0 divisors. Do we like building Z6? And the answer is, yeah, we can build it, but this is not cool. That causes it lots of trouble. In fact, linear equations have many solutions. So when we build these numbers, we never want to build them with reducible polynomials so that our extension or our quotient is a bad number system. We want the number system to be beautiful. In fact, irreducibility, field here, causes all of this to always be a field, and the numbers are nice. All right, here we go.